In this clip, we will explain why the Lagrangian method to find constraint optima works. And we're going to start out with a graphical representation, and in particular with the question, what constraint optima have in common. So we have two arguments. We have bivariate optimization problems. Input arguments are x1 and x2. And the function value is described by this contour plot. So f x1 and x2 is our function we want to optimize, to maximize, and graphically lighter colors represent higher function values. So we want to find the place on the function which has the lightest, the highest value. Here we are working with two examples, example A and example B. If we look at the example A and look at the contours of that function, you can perhaps imagine or perhaps believe that this function is quadratic in the input arguments x1 and x2. Whereas function B has these straight contour plots and level curve, straight level curves, and therefore the function is actually linear in x1 and x2, so it's actually a plane in the three-dimensional space. So what about the constraint? We said we're looking at constraint optima. As you can only actually see parts of these contour plots. So the difference between the white and the colorful area is that different input combinations are allowed and others are not. So here the ones with white, x1, x2 input combinations which are in the white space, they are not allowed, whereas the others are allowed, as is the boundary. So the boundary is also allowed. So this red curves or functions represent the constraint under which we are trying to optimize the function. Let us begin by identifying the constraint maxima graphically. This green points here represent the lightest area in our function f, which are allowed under the constraint. These are what we call the constraint maxima. And let's go back to this question of what do these constraint maxima have in common. And what we're going to look at are these level curves. You can imagine a lot of level curves here. A few are drawn in. I'm drawing a few extra. And you can imagine that this function f has lots of these level curves also in areas where the constraint isn't given, so in the white areas. So you can imagine these level curves going on outside. And let me represent them actually in the constraint areas by just dashed lines. And then we have this one level curve which touches the constraint at our constraint maximum. So let's see whether that is a coincidence. Let's look at example A. Here these level curves continue in the constraint area as circles, and we have this one circle level curve which you can't see but perhaps imagine, which touches the constraint exactly at the green point. And these green points, remember, are our constraint maxima. So what these two examples at least seem to have in common is that at the constraint maximum, the slope of the function's level curves, as expressed by dx2 over dx1 in terms of the units of how we measure the slope, is equal to the slope of the constraint gx1, x2, also measured in dx2 over dx1. So this is what both of these pictures have in common. At the constraint maximum, the slopes of the function's level curves is equal to the slope of the constraint. At this stage, this is a purely graphical argument, and perhaps we were just lucky that for these two examples that was the case. So what we're now going to do is we will first establish how to express this condition, the equality of the slopes, algebraically, and then we will establish why this will always have to be the case at a constraint maximum. So let's first find algebraic expressions for the slope of the level curves. So let's start with the slope of the level curves, and then we will look at the slope of the constraint. A level curve is that function that you get when you set the function, the bivariate function with x1, x2 as an argument equal to a particular level c. Okay, and then we're basically asking which combinations of x1 and x2 deliver exactly that function value, any sort of arbitrary value c. What we are really after is the slope of this function. So what we're going to do is a little trick, and it's an application of the chain rule. We're going to take this function c equals f of x1 and x2, and we're going to calculate the derivative on both sides with respect to d1 x1. So that's what we have here. So the green is just a derivative operator with respect to x1. Now on the right hand side we have a function which is a function of x1 and x2, so we will form the following. We take the first derivative with respect to x1 and plus the first derivative with respect to x2, so f prime 2, but times dx2 over dx1. We also sometimes call this the total differential. So here we have on the left hand side a derivative with respect to a constant. That of course will be 0. Then on the right hand side we have the partial derivative with respect to x1 plus the partial first order derivative with respect to x2 times dx2 over dx1. And dx2 over dx1, that was really the term we wanted to have, because that is an expression of the slope of the function. So we solve this equation for dx2 over dx1, and what we get is negative times the ratio of the first order partial derivative with respect to x1 over the first order partial derivative with respect to x2 f prime 2. So what this is really an expression of the slope of our level curves. There's a slight caveat that works if f prime 2 is not equal to 0, so it doesn't work at every point, but almost all points. So what we have is an expression for the slope of the level curve of f at a particular point x1 and x2. Let's do the same for the constraint, because we saw that the slope of the level curves is equal to the slope of the constraint at a constraint maximum. So here is our constraint equation, and we're looking at the margin of the constraint, not the inside of constraint, just at the margin, and that's why we have g of x1, x2 is equal to 0. We're basically applying the same trick here. We're taking the derivative with respect to x1 of both sides. I'll just switch the sides around, so we're having the derivative with respect to 0, and then the derivative with respect to g, the constraint which has x1 and x2 as an argument. The left hand side is 0 again, and on the right hand side we again get the first order partial derivative with respect to x1 plus the first order partial derivative with respect to x2 times dx2 over dx1. So again we solve this for dx2 over dx1, and what we get is the negative of the ratio of the first order partial derivative of g with respect to x1 over that same partial derivative with respect to x2. So we got now expressions for the slope both of the level curves and of the constraint. And what we previously saw graphically was that at a constraint maximum these two slopes were equal, were the same. So what we argued graphically is expressed in algebraic terms as negative of f prime 1 over f prime 2 is equal to negative of g prime 1 over g prime 2. So we started out with a graphical argument and then brought this graphical argument still essentially into an algebraic language, but now we want to figure out why that actually works. So let's go back to where we really started at, and that is a constraint optimization problem. We want to maximize a function f subject to a constraint g. And now we're going to think of the binding case, okay, where g is equal to 0. So what we're going to start out with is the following. We're going to solve that constraint function g for x2. So we get some function x2 is equal to gamma x1. So this is all abstract. You just have to imagine we solve this when there's an x2 in this g constraint, and we solve that constraint equation for x2 and we get some function of x1. We haven't really changed anything substantially. What we then do is we impose this constraint onto the function which we want to optimize. So we're going to impose this onto f(x1), x2. So we'll get f is a function of x1 and x2, but now rather than stating x2, we use the imposition that x2 ought to be on the constraint, and if x2 is on the constraint, it is the function gamma x1 of x1. So what we basically have done here is we formulated a constraint problem as if it was an unconstrained problem, because we incorporated the constraint into the function itself. Why does that help us now? Well, it helps us because we are sort of now just applying the well-known techniques of unconstrained optimization. So let's restate the problem in its slightly changed form. We want to maximize the function f(x1) and gamma x1, which really we should recognize that this is really now only a function of one argument, x1, so we call it phi x1. It's just some reformulation, acknowledging that there's really only this one input argument, x1. Let's find the stationarity point to this function, or points. So what we need to find the stationarity point is, of course, the values of x1 which satisfy that phi prime x1 asterisk, that's at the stationarity point, is equal to 0. So this just well-known condition for stationarity points. So what we need is we need to find out what phi prime is. So we will apply the same trick, calculating the total differential, just with a slight twist. So here we're calculating d over dx1 of that function phi x1. But now we recognize that phi x1 was really exactly the same as f x1 and second input argument gamma x1, which is really x2. So we're going to write f prime with respect to x1 plus f prime with respect to x2, so the first order partial derivative with respect to x2. But now we got to recognize that here, applying the chain rule, we really need to multiply this with d of gamma x1 over x1. And gamma x1 is really x2, as you see from the green highlight before. So this is like saying dx2 over dx1. which should make the chain rule application more obvious here. So we just stated that at the optimum we need the change in the function phi x1 with respect to dx1 to be equal to 0. We want a stationarity point. So from that follows the following. We have 0 is equal to what we have on the right hand side. But as we're now talking about at the optimum, we're now going to use as coordinates x1 asterisk and gamma times x1 asterisk, which of course isn't anything else but x2 asterisk. So f prime 1 of x1 asterisk x2 asterisk plus f prime 2 evaluated at x1 asterisk x2 asterisk times the derivative of gamma x1 evaluated at x1 asterisk with respect to dx1. Let's call this equation the hash equation, and we're going to continue on from here. Let's just create a bit more space. We now ought to recognize that of course gamma x1 asterisk is nothing else but x2 asterisk, the x2 value at the optimum. And remember, that's at the constraint optimum because we imposed the constraint. So gamma x1 was really just this reformulation of the constraint equation. And that's the one which we had imposed into the function f to ensure that what we find is the maximum value of the function f as long as we are sitting exactly on the constraint. So therefore, really, when we are looking at d of gamma x1 asterisk over dx1, what that really is actually the slope of the constraint at our constraint optimum. And we calculated that before. That is the ratio of the two first order partial derivatives and expressed in units of change of x2 over units of change of x1. So let's sub this into our hash equation. So we replace d gamma x1 asterisk over dx1 with our slope of the constraint at the maximum, at the constraint maximum. What we end up with is this following relationship. 0 is equal to f prime 1 evaluated at the constraint maximum plus f prime 2 evaluated at the constraint maximum times negative of the ratio of g prime 1 over g prime 2. All we got to do now is we got to solve for a left hand side which reads as f prime 1 over f prime 2, and if we do so we get on the right hand side g prime 1 over g prime 2, all evaluated at the constraint maximum. This relationship, of course, looks terribly familiar because it is exactly the relationship between the first order partial derivatives of f and g which we established after looking at the graphical commonalities of constraint maxima. The ratio of the first order partial derivatives in the f function are identical to the ratio of the first order partial derivatives in the g in the constraint function when these two ratios are evaluated at the constraint maximum. So what we basically have established now is that what we concluded graphically is actually universally true at all constraint maxima. Through the argument, the algebraic argument, we did here. So what is the Lagrangian method? The Lagrangian method is really just a tool to find the values of x1 and x2 which meet this condition. And if they meet that condition, we call this pair of values x1 asterisk and x2 asterisk, because they are the values at our constrained maximum. So without going into any detail of the Lagrangian method, we will just outline here how the method achieves that, or why it achieves that. When we do a Lagrangian optimization, we formulate the Lagrangian function, which is the function to be optimized, plus some parameter lambda times g. Then we form the first order partial derivatives of that L function with respect to x1, that's this one, and with respect to x2, that is this one, f prime 2 plus lambda times g prime 2. So here we have this new coefficient, this parameter lambda. It's sometimes called the Lagrangian multiplier. We want to set both of these equal to 0 as we are looking for optima. And when we solve both of these terms for lambda and then equate these two resulting terms, what we then get is the ratio of f prime 1 over f prime 2 is equal to the ratio of g prime 1 over g prime 2, which is of course exactly the condition which we derived previously as being the condition which got to be true at a constrained maximum.